Hi there, welcome to this lecture series on matrix algebra. This is part 2 of lecture 9. The topic is vector space. So in the first half, we introduced the definition of a vector space and some properties with some examples, and we also introduced the zero element. In this second part, we will go through subspaces and give examples and talk about concepts as intersections and unions. Okay, let's get started. Okay, first let's define what is a subspace, a vector subspace. So from the word, you see that there are two parts that stands out. One is it's a subspace, and the other is it's a vector subspace. Okay, so now let's say V is a vector space that's given. And then we look at a subset, we call it W, which is a subset of V. And this is also a vector space. And then this is called a subspace of V. Okay, so two things. It's a subset, and itself also forms a vector space. Therefore, we can say W is a subspace of V, then it will have the following properties. That is, now first, if two elements U and V are both in W, then I can add them up and it's still in W. And second, if U is in W and the C is a real number, and then C times U is a W. Okay, so this actually shows that W is a vector space itself. Now let's go through several examples of subspaces. And we're not going to give a detailed proof because it's a rather simple proof. So the first one is the set. Let's say we're given a set V is the vector space of all 3 by 3 matrices. And then we can take a subspace of it and take out all the symmetric matrices and form a set. We call it W. It's a 3 by 3 symmetric matrix, and this is also a vector space. Therefore, it's a subspace of the space V. Our next example goes to functions. Let's say we have a space of all continuous function, and then we take a subspace from it. That is, we take out all the polynomials. Then this set, we call it W. It's a subset of V. And then we also know from our previous discussion that this also forms a vector space. Therefore, this is a subspace. Okay, so we can take the space here as the big one. So let's say now V is a space of all polynomials of any degree. And then we can form a subset of all these polynomials and take out all polynomials of degree less than or equal to. And then we call this W. So W is a subset of V, and we also know that this is a vector space itself, and therefore it's a subspace. Okay, now some less trivial example. Let's consider the vector space V, which is all the vectors as in dimension 2, so all the vectors have length 2. Then the set W of all vectors such that the first element plus the second element, they add up to 0. And we claim that this forms a subspace of V. Let's see, we can get a little proof or a little check. Okay, so let's take two elements, x and y, with elements x1, x2, and the y is y1, y2, and they are in the set W. What does that mean is that x1 plus x2 is 0 and y1 plus y2 is 0, well, because that's the property of the set W. So we need to show two things to check this W is a vector space. That is, if I add up two elements, it's still in W, and if I do a scalar multiple of it, it's still in W. Now let's verify each of these conditions. Okay, so this is true. Let's check the first one. Is this element in W? Well, we need to check if the sum of the two elements are 0. So the first one here plus the second one here, they shall add up to 0, which is true because x1 plus x2 is 0 and y1 plus y2 is 0, and therefore it's 0. Okay, and then the second one, we want to show this is in W. That is, the first element plus the second element shall be 0. So we want to show that, well, which is true because you can take out C as a common factor, and then you have x1 plus x2, which is 0, and then it's 0. Okay, let's take some examples that is not a subspace, which it's a slightly subtle concept here. Okay, so the set W of all polynomials exactly degree 2. Okay, so which means the polynomials, the p in the W, can be written as ax squared plus bx plus c, where a is non-zero. And then such a set is not a subspace. We can just take one example, and that violates the condition of being a vector space for the W, and then we're done. We now take two polynomials of exactly degree 2. P looks like that, and Q looks like that. We know that the coefficient in front of x squared is not 0, so it has degree exactly 2. And what is the polynomial P plus Q? If you add them up and you see that the x squared terms, they cancel each other, and we only have 2x plus 4x, which is 6x, plus, and these two add up to 1. And this is a polynomial of degree 1, so it is not in W. So we found an example where P and Q is in W, but P plus Q is not in W. Therefore, this W here is not a vector space. One more example of not a subspace. So let's look at the set of all vectors with the property that x1 times x2 is 0. And we show that this is not a subspace of all vectors in R2. Indeed, we can find two elements. One we call x, which is 3, 0. And then the second element y, which is 0, 2. So we know for 3, 0, 3 times 0 is 0, so this is in W. And then for y, and 0 times 2 is 0, so this is also in W. What about x plus y? So if I add these two up, I will get 3 and 2. And then 3 times 2 is not 0. And this is not in my subset W. And therefore, the W is not a vector space. If you have two sets, you can find the intersection of them. The concept of intersection can also be introduced to subspaces. And in fact, we have this theorem here. Let V be a vector space, and then we find two subspaces, W1 and W2. They are both subspaces of V. Then the intersection W1 intersect W2, that's the notation. Then the intersection is also a subspace of V. Okay, and we will go through a little proof for that. And just a word of caution in regard to the concept of a union. So we also know if you have two sets, you can find the union of it. We just want to point out that the union of W1 and W2, it may not be a subspace. Now let's go through a proof of the theorem of the intersection. Okay, so now let's introduce two elements, U and V. They are both elements in the intersection of W1 and W2. And in order to show this intersection is a vector space, we need to show that the sum of U plus V is in the intersection. And if you multiply a U by a real number C, it's also in the intersection. Okay, let's go through these proofs. So we know that U is in W1 because U in the intersection, meaning U is in both W1 and W2, right? So U is in W1 and V also is in W1. And W1 is a vector space, and therefore U plus V is in W1. And we can do the same argument for when they are in W2. So now U is also in W2 because it's in the intersection, and V is also in W2 because of that. And W2 is a vector space, and therefore U plus V is also in W2. And now what have we concluded? Well, we found out that U plus V is both in W1 and in W2, and therefore it's in the intersection of W1 and W2. Okay, and the second property is easy. So U is in W1 and U is in W2. So because W1 is a vector space, and therefore this would imply CU is in W1. And then W2 is a vector space, so this would imply CU is in W2. So CU is both in W1 and W2, and therefore is in the intersection. Okay, so this completes the proof. We now take an example of a union of two subspaces, and let's see what happens. So in the vector space R2, we now consider two subspaces. One is W1. Okay, so a little bit of a notation. We write it like this. So this means it's a set of vectors like this. The second element is 0. The first element is just A, and this A can be any real number. Okay, so in other words, this will be set of all vectors whose second component is 0. So try to get used to see a notation like this. Okay, and for W2, it will be the set of all vectors in R2 where the first element is 0, but the second element can be just any real number. Okay, so this will be set of all vectors whose first component is 0. So, okay, so and all that words can be written in symbol just like that. Now let's look at the union, and then we want to show that is not a subspace. For example, let's take an element 1, 0, which is in the union of W1 and W2 because it's in W1, therefore is in W1 union W2. And then we look at another vector 0, 2, which is in W2 and therefore is in the union. And now we can perform the summation, this element plus this element here, and then we get 1 and 2. Okay, does this one lie in the union of W1 and W2? Well, No, it is not, right? So W1 is second element is 0, W2 is first element 0. So the union would be the set of all vectors, either the second one is 0 or the first one is 0. At least one of them is 0. And this is not. I have 1 and 2, none of them is 0. Therefore, the union is not a subspace. Okay, let's look at in R2, and there are some observations about subspaces. So in the vector space R2, every line through the origin is a subspace. So we have a graph here, so let's draw the coordinate x1 and x2, and we consider all vectors along and all the points on the line through the origin. So you can see that if you have a u and then you have a v, and what is u plus v? Well, that is you take u and then you continue with the same direction of length v, and it's still on the same line through the origin. And then now if you have a u and you do a scalar multiple of u and you just like rescale this vector, it's pointing in the same direction. Okay, so therefore this is a subspace. However, if you take a line that does not go through the origin, then all the points on that line is not a subspace. Okay, let's take an example here. Let's consider a line like a horizontal line with going through anything, 1 for example. And now we have one element, which is u, so it's a vector pointing to the end point on this line. And then we take another point, v here, that's the second vector. And what is u plus v? Well, you would take the end point of v and form this parallelogram, and that point will be u plus v. And then we see that is no longer on this line, we call S here. So u plus v will not be an element in the subset, and therefore this is not a subspace. Okay, the observation in R2 can be extended to R3 in a vector space of R3. That's the three-dimensional space we are living in. And we know that every line through the origin is a subspace. So if you take a line through the origin, all the points on that, that's the end point of your vector, and they will form a subspace. The argument is exactly the same as in R2. So you have one u and one v, and you add them up, it's still on this line. Okay? And second, now since this is a 3D space, we can have a plane going through the origin, and that is also a subspace. So imagine you have a plane and it goes through the origin, and then you have an element, two elements u and v in the plane. What will be the sum of these two elements? Well, the sum will be this one. It will be in the same plane as u and v, and therefore it will also be in the w. Okay? All right, so, and then similar to 2D, if you have a line or a plane, but they do not go through the origin, then this is not a subspace. Okay, a similar argument as we have done for the 2D. Okay, so that's all for this lecture on vector spaces. Next time we will look into the concept of linear combination. I hope you enjoyed this one, and I'll see you next time.